Welcome back, everyone. So in this video, we're going to be looking at how we can take a spring system like this and calculate just a few different examples, right? I obviously can't get to every single type of problem, but these are some basic ways. Obviously, some are reversible, which I'll explain as we go along. So what's our system? Well, we have a spring attached to a wall, and on this end, it's attached to a 3 kilogram mass. Okay? There is no friction between the block or the box or whatever we want to call it and the floor, the horizontal floor. Not a good drawer. The spring constant of the spring is 250 newtons per meter. Okay, and at this point here, at our equilibrium point, the speed is 1.7 meters per second. Okay, here at equilibrium point we say x equals 0. Out here we say x equals x equals negative x. Right, so this way is positive, this way is negative. All right, so what are we going to look for? Well, first we're going to find out what is the magnitude of that amplitude. So when it's here or here, what number would we say x is equal to? Acceleration at your amplitudes. I picked just our positive. And then the period of the whole system. So how long does it take to get from here and back? All right, so let's take a look. Well, if we want to find the speed, if we want to find our displacement, our amplitude, our maximum displacement, we can use our speed and conservation of energy to help us figure that all out. All right, so let's check this out. Here we have a maximum kinetic energy. Here we have a maximum elastic potential energy. Since this is a closed system, conservation of energy rules, and the amount of energy here in elastic potential equals the amount of kinetic here. So we do this. 1/2 kx squared equals 1/2 mv squared. Okay. Our 1/2s cancel, so we're left with kx squared equals mv squared. Okay, we're looking for our x. So let's plug some stuff in. Well, our k is our spring constant. That's 250 newtons per meter times x squared equals our mass, 3 kilograms, and our speed, 1.7 meters per second. Don't forget to square it. Okay, do some calculations. So 3 times 1.7 squared, all divided by 250, and then square root, we find our x to be 0.186 meters. All right, so from here to here is 0.186 meters. And since there's no friction, there's no dampening, this would be negative 0.186 meters. All right, now let's find our acceleration. Once again, since there's no friction, the forces at work here, well, we have gravity down, normal force down, but it's only moving horizontally, so there's no vertical acceleration. So the horizontal net force is that Hooke's law force, F equals kx, which also, in our case, will equal ma. All right, well, we know our k is 250 newtons per meter. Our x is what we found in part A, which is at 0.186, 3 kilograms for our m, times a. Okay. Do a quick calculation. We find that our acceleration out here is 15.5 meters per second squared. Right? This is the magnitude of our acceleration. Okay? Direction out here for our acceleration will be actually pointed this way because it's starting to go this way. If it was here, it'd be going that way. Okay? All right. And finally, the period of the spring. Well, let's look at our equation for that. T sub s equals 2 pi times the square root of mass divided by spring constant. All right, let's plug our values in. 2 pi times the square root of 3 kilograms for our mass divided by our spring constant, 250 newtons per meter. And doing our calculation, we find that the period is 0.688 seconds. Okay, so there we go. Again, these are some basic types of problems you could see, right? If we were given this amplitude, we could then find the speed using the same process, just change which unknown variable it is. And then we kind of go from there. If there's friction, right, you have to do a little bit more to it. But we're not going to focus on that here today. All right. I'll see you next time.